Okay, I think now I shall wait for only 1 minute now. Okay, then onwards I'm going to lock the meeting and then we'll be starting for the class. Be aware onwards. I'll not let anybody to enter after 5 minutes of the class. Right. So let's come to the discussion. So what we have started in the last lecture for discussing on is the different kinds of errors into the measurement system. And we have first of all say our first objective is to identify what are the different kinds of the error that can occur and what can be reason for those errors. Okay, once we have understood that the types of the errors are going to occur, the nature of the error is clearly known, then we'll be able to understand and take care of that. So I think in the last lecture we have also seen the calibration, something very brief about calibration, right? So that calibration, or say establishment of the accuracy of the system or performance of the measurement system, can only be done when we take care of the errors that are going to occur, the reasons for giving the say readings which are not very conforming to the true input that is given to the system. I hope objective of this is very clear to you. The objective of the measurement that we are going to carry out, the error that we are going to find out. Am I audible to you all? Let me know, please. Now I think the time is up. There is no 11:06 a.m. Right. So let us now see the types of the errors that can be introduced into system. As we have seen in the last class, we'll very quickly recap. The types of the errors will be, what is the error? First of all, is difference between the measured value and the true value. There can be systematic or cumulative error, there can be random error, accidental error, and there can be miscellaneous types of the error which cannot be grouped between the types of the systematic or the random errors. Then we have seen that systematic error is because of the instrument error or environment or loading error. And what is the peculiarity or very important part of this is, it can be made known, say after having the consistent reading or through the proper process, we can know this. So you can have elimination, corrections or calibration of the systematic error, where a random error is one that can be found out by means of averaging. Maybe because of the inconsistency with the accurate measurement system of the small quantity, there can be system defect, there can be uncertainties and randomly varying parameters. So by averaging, we can at least take a note of what is the random error. So averaging is nothing but the tool that is used from the statistics. So by having the different techniques, statistical technique, we can come to know about the random errors. So let us understand the types of the error. I think we have gone through this in the last lecture in detail. Systematic error, right? So instrument inherent error due to the poor design, construction, configuration, and the stages, the improper staging into the measurement system. It may be because of graduation of the scale, balancing of the arm, irregular spring tensions. Now, one thing we have not discussed in the last lecture, into the multiple staging, say for example, primary sensing element, variable conversion element, variable manipulation element, and so on. There can be different components introduced into, say example that we have seen in the case of amplifiers, in the case of the rectifiers, in case of some say electronic circuitry that we are going to use for having the proper readout of the output. So in that condition, right, now I am going to lock the meeting now, right? It's already 11:09. So I should lock now. Nobody should be entering into the class now, right? So into this, that's what we said, because of the staging or the improper design of the staging and the different circuitry, there can be, say, irregularities in the amplification of the signal, right? So that also is going to give rise to the instrument error. So the instrument error can only be knowable. So that is what we go for, say very careful designing of the electronic circuit that we are using into the measurement systems, right? So the error can be avoided by choosing suitable equipment for proper application, proper calibration, correction, and compensation, right? So okay, so let's come to the environmental and loading error. Environmental error due to the factors that are external to the instrument, like temperature, pressure, humidity, wind force, magnetic or electric field, even the gravitational constant, the orientation, and the other elements with which the instrument has not, say, by its inherent characteristics prone to this, but it's because of the operating conditions, the environmental and the loading errors. So the loading error, I think, is also seen. The loading error is very clearly known that the system is being given an additional disturbing signals than the input signal which are present originally before applying the measurement instrument. So equipment loads the system, and due to the measurand or the quantity to be measured is changed or altered. So it is obstructing the flow meter, thermometer alters the thermal capacity, and so on. I think one simple example that I have given, measurement of the size of the eraser by applying larger force on the jaws of the vernier caliper, we see that there is compression and it alters the original value. So this is another effect. One effect is because of the temperature used as an entity for the thermometer, there is reduction in the temperature of the system. Here there is reduction in the size. So these errors can be either eliminated, corrected, or calibrated once we know what is the extent of the environmental and loading error that is going to occur. Right. Say for example, in earlier case, I think in the compass, there are different methods of correcting the input. We have found that method of calculation. We find out what is the temperature, the linear expansion of the scale, linear expansion of the device length because of change in the temperature, because of change in pressure, and so on. So this is how we have quantified, and then we can make the correction. Right. This also has been discussed in the last lecture. Then random errors are the inconsistencies associated with the accurate measurement of the small quantities. The quantities are small, then that will be a random value. It will be taken to contribute as. I think I have given example of, say, readout if it is a 0.5 on the scale. Say this is now 1.5 and 1. These are the 0. These are the graduation. And if the quantity is little less than 0.5, one can count this as 0.5 or 1 or say 0. If it is little higher than 0.5, say one can guess is approximately 0.6. He can call this as 0.5 or he can call it as 1. So then there will be error. It is actually not correct because it is somewhere here, and one of you is taking this as equivalent to 1, rounding off to 1, one of considering this as round off to 0.5. In both way it is going to be wrong. So that is nothing but a random error. So while measuring the quantities, small quantities, random errors do not give consistent reading. Interpretation may be wrong. So error because of the error becomes noticeable by measuring the quantity which are of equivalent magnitude. So often, if suppose this kind of input is applied, then we only will come to know that no, it is actually 0.6 or it is 0.75. So it is improper to call that as 1 either, or even improper to call it as 0.5. Right. So this is something called as a random error. So it is because of the system defect. Large tolerance on the dimension, friction, clearance, backlash, slackness in the meter reading, measuring the quantity first while increasing and then decreasing the magnitude. So ascending and descending, we apply and then we see what is the conformance between the two readings shown. Right. So in this way we can come to know there are defects or some other factors which are responsible for the randomness. So effect of the undesired and the randomly varying parameters. So it is a voltage fluctuation, variation of the instrument supports, and so on. Right. Now let us see miscellaneous or the gross type of error. Those may be because of the personal or human. I think this was not discussed in the last lecture. Let us discuss from here in detail. So personal or human error. Right. So this is a limitation of the human senses to take the reading and interpret that. Right. Say for example, the same process of having the temperature measurement is done by operator number 1, and now the same entity, same input is given and same entity is asked to be measured by operator number 2. Then we find that there is difference between the readout, the expression of that, the interpretation of the output shown by the instrument. So these are personal or human error. Right. So there is variation of reading, method of conducting the measurement, then interpreting that. Based on that, the calculations are to perform. If somebody is taking say up to 3 decimal correction, values will be something different. If it is somebody is taking 4 decimal points into consideration, the accuracy is something different, and so on. That also depends on the expertise. Say, for example, very simple way we can see if the diameter of this component is measured by using vernier caliper. Whether I am going to take the vernier caliper so that it is going to be perpendicular to this, or then I am going to consider this as tilt. So if it is tilt, then say this is the very simple way of knowing what are the different errors that can come into the, say, if I am going to consider the vernier caliper like this, then the jaws of vernier caliper, they will not come in proper contact with. Say one jaw will touch here, the second jaw will touch here, and because of which I think the dimension will not be correctly measured. Right? So this is what is the method. It depends on the person, how willingly, how aware the person is while taking the measurement is also known to. Say for example, the meter, if there is some meter, the pressure gauge that is showing the pressure, if it should be very parallel to the face. The pointer should be very parallelly visible, so called as a parallax error. If I am going to consider my viewpoint exactly in line with the dial, then probably I have a proper way of matching that to the scale. But if I am going to look, the pointer is here and I am going to look from the angle, then probably this may coincide with another graduation, either this one or this one. So these are how the error, because of the person has introduced into it. And here, that is the reason that we try to avoid this human part of either reading or interpreting the results of the measurement system. So error due to the faulty components of the adjustment, that is also possible. So misalignment of the moving component, then there can be electrical leakages, there can be poor optics. Say especially in case of the electrical leakages, if the circuit has got different ground points and all ground points are connected to some other equipments, say possibly there is a loss of electron between the measurement device and the one that is taken as earth. So you find that there is, say, some charge lost into this. So that may cause the change into the error. So that is the reason we need to isolate properly. I think method of filtration is somewhat similar to this, the method that we are studying in some earlier classes. Right. Then it can be poor optics. That's what I have said. So optical devices, if I am not using properly, I am not aligning the scale which is used as a reference with my eyesight, the operator's eyesight, again it is not going to give proper reading. So it is poor optics. So it is because of the faulty components or adjustment. There are suppose 2 optical scales. If those scales are not aligned properly, the center of the scale 1 or disc 1 having the graduation on that, and disc 2, if they are not aligned with the center, then probably there will be a mismatch. You can imagine now, say for example, the optics disc 1 is having some graduation on that, and then disc 2 is also having some graduation. This is now made fixed, and suppose this is, say for example, the torque measurement device. This is what I am going to apply some torque on. Because of this, the disc is supposed to move related to this, because this is going to remain fixed. And if there is an eyepiece, if the centers are not aligned properly, then it won't have any proper match. So that is nothing but optics. It is misalignment of the centers of the 2 discs. So that is going to generate some kind of error. So that will be inbuilt error into the instrument. Right. Then it is an improper application of the instrument. So using equipment which is not designed to be used for that. And then presence of vibration, shocks, electrical noise during the measurement environment. So improper application of the instrument. Say the instrument is not made for measuring the given entity, but we are applying that. So these are the miscellaneous type of error which can be avoided by means of the skill, improvement in the skill, or knowing the system properly. The knowledge of the measurement system, its functioning, the factors which are affecting the performance and so on, if it is known very clearly, then we can go on gradually reducing this kind of error. But definitely this error can be nullified It can be nullified only if we try to remove the human part into this one, try to remove the adjustments into the instrument. If we try to select the proper instrument, or the instrument can be designed, say for example, for measurement, and that is what now we have got a very good say process. We try to select the instrument which is very required for the given measurement. Say for example, accuracy of 0.001 millimeter is required in the measurement of the dimension of this particular bar, round bar on the lathe machine, say for example. Then the instruments are very properly and very carefully selected, which have got the minimum measurement value of 0.01 millimeter. Then only can ascertain the proper measurement in the measurement, so that the instrument which is required for this task is only selected here. Right? Any doubt to this point? Right. Then let us understand the discussion. We have seen that there are basically three types of errors: systematic error or cumulative error, random errors or accidental error, and the miscellaneous types of error are the gross errors. So let us understand first what is the nature of this kind of errors that are going to occur. So to know this one, we are going to assume the very simple application. That's now I have said. This application is about having the measurement of some dimension. Now before starting the measurement, if I make this job, the caliper to match with this, I can find that it's going to show something value as even with zero reading. Now what has occurred because of this, there has introduced an error which is going to last long for any of the measurement of the diameter of the length in between the capacity of this particular measuring system. So suppose now there is one 5 millimeter bar I am going to keep, it will show 5.002, or if it is minus value which is showing, it will be 5 minus 0.002 as the reading output shown by the equipment. If it is 10, it will be plus 0.002 or minus 0.002, what it is shown here as per the sign. So that is what that error is going to remain constant throughout the use of this measuring system. I think this is very clear to you. This is what is we have defined as a systematic error, is going to act as a cumulative error. The error because of all the sources. For systematic error, they are going to have common sign, the similar sign, and similar entity, the magnitude. So it will be added numerically. Right? It will be algebraic sum. That's what we have said. So once we know the meaning of the nature, the systematic error, how it occurs into the system, then we can say that the systematic error is caused by the factor that systematically affect measurement of the same measured performance or same measurand, same input under the same condition. So for example, the 5 millimeter bar is measured at 20 number of times using this particular equipment or measurement device or measurement system. It is going to show more or less the same reading at the output. So systematic error is caused by any factor. That's what we have studied earlier into the slides, that systematically affect the measurement of the same measurand where the measurement activity is performed under the same conditions or repeated number of times. So this reference, whatever I am discussing onwards, is taken from the Handbook of Measurement System Design, Tata McGraw-Hill book, and their title of the topic is General Characterization of the Systematic and the Stochastic Errors, page number 297. So what it says, that as with all this kind of error, systematic error also arises because of the four main sources. The sources that we already have studied in some earlier slides here in this particular topic. So the method of measurement is very, very important for knowing the systematic error. Say for example, improperly selected method. I have given one example just now, that the diameter of the bar, if is to be measured by using the vernier calipers, and if I am not going to keep the vernier caliper perpendicular to this, then jaws if it's not perpendicular, then jaws will come in contact with the entity here. So this is what is contact, and definitely it has shown some larger distance. The desired distance for measurement is this one, but this length is larger. This is L dash or D dash, I should say, and this is D. So where D dash is going to be greater than D, this is what we have seen. So this is the effect of the method that I am going to apply for measurement. So measuring method is very important. Say selected methods affect the measurement the same way. So for indirect measurement, this is for direct measurement, where the measurement system is coming in contact with the entity under measurement. Right? So here it is going to play a role also into the indirect measurements. Rounding or uncorrected values of the constants are often used. We notice that. So for example, very simple example of pi is 3.141. Somebody can take 3.14157 to the further digits, or improper gravity's, say, acceleration rate g. The value of g is 9.81. Actually, it is 9.801 something is there. I think you might be knowing this correctly, up to say 5 digit, 6 digit. So if I round it up to 9.8, it's going to give some different effect on the measurement. So that is what is a measurement method. It is very, very important. We do not come to know the effect of the measuring method, improper measurement method, on the systematic error. Then the next source is the measuring instrument itself. That's what we have studied. The error due to the instrument. Systematic error causes constant difference of the calibration curve from the characteristic curve. So the difference between the calibration curve and the characteristic curve. Characteristic curve is nothing but a curve that is really obtained, or say that is obtained actually. Actual curve or actual performance characteristics during the measurement process. Whereas calibration curve is the one that is a very standard curve available from the manufacturer. So when we purchase any measurement system, we have given the attributes of the system, that our system is accurate up to say this much value, say plus minus 0.0 or something, some value is specified, and then characteristic curve is also shown that this system is going to behave linearly up to this value of input, then little deviation, like that. Whatever the characteristic, this curve is specified by the manufacturer, that we call as a calibration curve. That is to be established often by means of the calibration. So that is what the frequency calibration is required. So then the error causes difference. There is always difference between the ideal curve of performance and the actual curve. Similarly, the conditions in which measurement is taken. Measuring instrument being used in the condition which are differing from the one specified by the manufacturer. So manufacturer considers that instruments are used in controlled ambience. So for example, temperature, pressure, and all other conditions which are specified in the standard condition, in which these curves are, say, calibrated and attached to the instrument or the measurement system. But in actual practice, wherever we go on actual having measurement, those are different from the ideal conditions. Right? And then the last one is, I think this is very common, this is known from earlier slide, that the temperature is most common, which is going to affect. Pressure is also going to affect. Then gravitational constant is going to affect. Presence of the electrical and electronics noise signals, the AC fields, then some kind of radiations, if those are present, some kind of magnetic device in between present. So these are the conditions. And then the operator. I think this also we have seen the personal error. For example, wrong reading from the line scale. So use of some, instead of analog or digital indicators, are going to avoid these kind of things. So digital indicators avoid the error. Right. So these are the nature. Once we understand the nature of the systematic error, we'll be able to take care of that, how to take that into account. So theoretical divisions of the systematic error states that the two categories of the systematic error exist. Now let us understand the objective. Till this point of time, earlier we started the nature of the systematic error and study on that. Our objective was to know what are the different errors and how those errors are going to affect the measurement process, what can be causes of that. Now we have moved ahead. If at all some kind of sources of systematic errors are present, how that can be taken care into the measurement and how we can have the proper estimation of the true value that is actually applied to the measurement system. That is the objective now. So in relation with this, we must know what is the nature of the systematic error and how that is progressing or how that is attributed as an error source or calculated as an error source afterwards in the measurement process. Say this is how you are going to calculate. Some equations are something is given in your practical that you have to calculate the accuracy, full scale, true scale. You have to calculate bias, linearity, non-linearity, and other things. I think those are given to you. You need to understand that you have carried out the measurement process. You have got the measurement. Now let us understand whether there is some inaccuracy present in the equipment. Is it because of the systematic error? Right? That is our objective now. So through this objective, we will try to see the division. Or basically, the systematic error can be attributed to two different ways. One is additive systematic error and the other one is a multiplicative. So the addition errors are those values that do not change with the measured value. Say for example, the readout that I have shown you in the earlier example. Say for example, there is a micrometer and to this micrometer, when you touch this to 0, the probe is touched to 0, the reading shown is say for example plus 0.002 millimeter. Now if I insert an element here of 5 millimeter diameter in between, the readout will be showing 5.002. If I insert the another element here of 10 millimeter diameter, reading shown will be 10.002. If I insert 15 millimeter bar in between to measure the diameter, it will show 15.002. So that is the meaning of this. The additive errors are those values that do not change with the measured value. Even if the input is changed or even if the input is going to mean same, it's going to show the same reading often. Say 5 millimeter bar diameter read, say 10 measurements are taken. At all the 10 times, those values will be very close to this 0.02 or exactly 0.002. 5.002, 10 times you will get as a measurement. Right. So these are the additive errors. These values are not going to change. This error value is not going to change even if you are going to change the input or even if you keep the same input and take multiple reading, it's going to be the same effect. Then multiplicative errors are those which change their value with change in the measured value. Right. So the most common additive, let us discuss this also. I am going to give some example for this. Say for example, now you are having the temperature measurement device, say a thermocouple junction for measurement of the temperature inside this system, which is kept at temperature T. Now, if you are adding some heat so that with respect to time, the temperature is going to change, say T from 0 degrees Celsius, say, or the initial temperature T0, it is going to take the form T1, T2, T3, and so on, say T10. There are 10 different values you are going to take after interval of 1 minute each. Once the heating is started, you are going to take the reading after 1 minute each. Then ideally it is required that it should show the actual heat content into the system. But because of different factors, you find that the reading will be differing. It will not differ with the linear, say, way, but it will differ with some other pattern. It will show some other reading at given interval time, say for example 1 minute, 2 minutes, 3 minutes, and so on. Required that it will show this reading. Instead it is showing this. So this is what is the meaning. Multiplicative error changes the values with change in the measured value, the input, if it is changed, I am counting this with respect to time. You can say correlate this with respect to the input, and then we can call this as the output change. So most common additive errors are the offset errors and the linearity errors. So this is what we can say, very guess. It is nothing but offset of the initial or basic reading, offsetted by 0.002 millimeters. Right. So this is what is the way we consider that input actual measurement. Like multiplicative errors are presented as a gain. It is nothing but something gain. Maybe because of some, say, unwanted values, it has shown a increment into the measurement. So that is nothing but kind of a gain. So systematic errors of the measurement system is manifested in most common cases by combination of these two, that is the additive and multiplicative, both we combine and then we estimate the type of the systematic error or the quantity of the systematic error that has introduced into the measurement. Let me know any doubt into this to this point. So what we are doing here, we are trying to understand how systematic error behaves into the system, and then we are going to take some corrective measures. Any doubt to this point? So what we studied in the 2-year lecture, that the random source of error, the miscellaneous type of error, what are the root causes of miscellaneous error into the measurement system, and then how now we are going to take care of these systematic as well as random errors into the actual experimentation or actual measurement of the entities. So we first of all trying to understand the nature of the systematic error. Then it can be of additive type or multiplicative type. Additive values do not change. Example I have given you. Multiplicative error changes with respect to the given change the input. Right. So it can be an unintentional gain, incremental value that are added into the output display of the measurement system. So systematic error of the measurement system is manifested in most cases by combination of these. So now we are going to combine these two. So for this we must identify, we must call those as correlated to some kind of errors. Like the first of all, just now we have said it is offset error and the linearity error. So we must understand how those occur, and then we must understand how the gain occurs. So we understand now first offset, linearity and the gain kind of error. So the offset error is one, going the difference under the specified conditions of the use, so that between the actual output value and the specified minimum value of the output range, when the input is at the lower range value. So to understand this, let us say the input, any input value it is given, we find it is going to have some kind of error. Say actual value or the true input is something given by the curve, and then the calibration curve. So sorry, the standard value is this one, but in actual value it is going to show something. So this is the difference that is going to remain at any point of time, say at any measured value. This difference is going to remain constant. Say if I am going to find this out for one input, for next input, say between this and this, if I am going to count, again the difference deviation will be the same, d. This difference is going to be recorded here, the same difference. That is what it has offsetted by the same entity over the entire range of the measurement. So for example, from 0 to 100 units of the input for which the instrument is made or the system is designed, it is going to have the same shift called as offset. I think this is very clear to understand now. Take an example, other example of the earlier example of your vernier calipers or the micrometer screw gauge for measurement, or say for example temperature measurement using thermometer, or say using the spring balance, force measurement by using spring balance. You take any example, say pressure measurement by using the bottom pressure gauge. The same value will be added over and above the standard input given. Say for example 5 bar pressure, it will have offset of 0.002 bar. So it will show 5.002 bar. If input is 10 bar, it will show 10.002 bar. It is going to make an offset. Right. So once we have understood this, we will be able to compensate that with some reason or with some process. Let me know any doubt into this understanding. What is the offset error? Now slowly you'll be able to understand what is to be done for calculating the entities that are asked into your say experiments. Okay. So I think you start writing down the experiments now, all the 5 experiments, and till that time I hope we'll be able to cover up the required theory for calculating the static errors. Right. So you at least start writing from theory point of view. You go and study the different equipments and start building up the theory. Whatever contents except the calculation part, I think you can write everything. You can start writing and drawing the circuit diagram and everything. So that it should not happen that if I am asking you to submit the journal say in a 2 days, you should not say that it is very say rush or say we are not having time for submission of that. It should not happen. You should go and start writing now. The portion except the calculation part and making the graphs. You can do all other things. So as and when we cover up this portion, I will be able to immediately declare that you have to submit the journals. So you keep a watch on that. You try to be say going with the experiments that we have conducted. And I also asked you that few of the volunteers can come down from your batches to perform the experiments. So if you are going to come here, it's fine. If not, whatever I have shown you, you will have to find out the readings out from that. Okay, so coming to the next, now linearity error we need to find out. So usually that offset error is expressed as a percentage of the specified span. Now how this is expressed, say for example, I have got a pressure gauge, a Borden's pressure gauge with me that is purchased from say market, and then on finding applying very standard input, say for example 2 bar pressure I have applied, and I have found that is going to reflect to say 2.01 bar. If I am going to give the standard input of 5 bar, it's going to show 5.0 bar. What is this value? Suppose full range from 0 to say 20 bar. Then I have to specify that the maximum offset error in this equipment can be some value of percentage of the specified span, say 0 to 20 bar. This is how we specify. You first of all calculate or we estimate the error and then we specify how much it can be on the given span of the measurement. I think this will again come across in the next slides. How to specify it and what is the meaning of the span. Okay. Then we come to the gain error. It is a multiplicative error. Just now we have seen measurement of the temperature by thermocouple junction. Say for given input, say for example, these are the inputs I have divided. Say input 1, input 2, 3, 4, 5. These are the different temperatures, let us say. Or these are the 6th value of the input temperature that I am giving. Actual practice, it has to show something which is related to the calibration curve, the standard curve that is given for the instrument, but it is showing something higher. Here it is small, it is increased. For the third, it is still increased further. It is increasing with some rate. So this is the gain error. So slope of the characteristic curve differs from that is of a calibration curve. So the absolute value of the gain error depends on the input value. Say if I am going to have smaller input, it will have lower gain. Little increment into the input, little increment into the gain, and so on. So it is proportionally increasing. Say it is going to have some incremental way, some fixed proportion in which the gain can be anticipated. The absolute value of the gain error depends on the input value. Relative error remains the same. Right. Then linearity error. Now because of the linearity, say into the characteristic curve that is given by the manufacturer of the equipment or the measurement system, it expects that it should have a very linear relationship between input and output. But in actual practice, it is going to differ. So for a given input, at any point of time, we can find out what is the error in the linearity, how much it has deviated from the linear curve. So when expressed as the linearity error, it is assumed to be independent of the linearity. the absolute value of the maximum deviation between the calibration curve and the specified straight line or the characteristic curve given by the equipment, say manufacturer. That is a linearity error. So we express again that in terms of the maximum non-linearity of the equipment is something in terms of the given range of measurement and so on. So this is a general way of finding. Let us understand now how the random error is going to behave. Say, first of all, we must understand what is the result. When a random error is found out, the reading is found out, the random error is nothing but the mean and the difference between, the mean value and the measured value. So it is the actually resulting out of the measurement. It is say quantified or say found out by having the difference between the mean that will result from infinite number of the measurements. Say the word is taken infinite. It means that sufficient large number of readings are taken for the same input. That would result from infinite number of the measurement of the same measurand carried out under the repeatability condition. I think this will define in the next class what is the meaning of repeatability and so on. So it means that in the given constant condition, we have repeated the experiment number of times. And then we have made known what is the output. Say some point of time it has shown, say for example here, input is 19.8, 19.9, 28, 20.1, 20.2 and so on. Say for example the input is given and number of times the output is given like this. Say 2 number of times it has shown this value, 3 number of times it has shown this value, 4 number of times it has shown this value and so on. So the finite number of the measurements can be made in practice. That is what I said. Infinite though it is said theoretically. We have to take sufficient large number of the readings. That is meaning of the finite number of the measurements. Therefore, it is possible to determine only the estimation of the random error, which is coming closer to the say estimation of the random error. We cannot find out a very correct measurement of random error. It is approximation always, right? So a finite number of measurement can be plotted then in the form of histogram that is already shown here. 19.8 shown at 0 point of time or 0 number of repeated values seen with this input. Twice this input is reflected. Then thrice this number of this input is reflected or output is shown by the equipment like that. So we are going to plot a histogram. So large number of the measurement then with accuracy will produce the particular histogram with a smoother shape. Earlier histogram can be say made in the form of very smooth shape, that is nothing but a normal probability density function in the form of probability density function. So for infinite number of the measurement and infinitely small intervals, this histogram transfers or transforms to a smooth curve that can be described by theoretical equation and be replaced by the probability distribution function. That is what is we know it. We once have the normal distribution function, we can go on applying some statistical methods for finding the random error. So measurement theory now most often assumes that the general Gaussian distribution, also known as a bell curve, can describe the occurrence of any given error. Say for example the variance and the standard deviation is found out, we can find out the probability that the error will be given about the mean value. So this is most approximate value of the true entity. And what is the possibility that the true entity will be indicated something in the form of error because of the random deviations is found out, right? So this assumption is based on the central limit theorem that does not necessarily always apply. So these are the statistical tests we conduct. Then there are different equations. We found out mean, mode, variance, standard deviation, and then 3 sigma limit. I think these are known to you now. So this way we'll see some numericals where the random error is to be found out, right? So I think this is something a very brief discussion on what is an error, what are the sources of error, how to avoid those, what those are contributed, and how those are. In very briefly, I have not discussed any say numerical, standard numerical, but how broadly that can be found out through the measurement is introduced to you. Right? Then we are going to see few of the numericals just when we understand the characteristics of the instrument. Now let me know any doubt into this. So very first message, I will again repeat, you should join as early as possible, well within 5 minutes of the class starts, so that now I am still finding few of the students are waiting in the lobby, and I have made it very clear, I am not going to let them in into the class. And normal instruction, you have to maintain 75% attendance, and then we are going to ask the scholars that they will randomly announce any 10 to 15 students to make videos on. If you are not going to make it on, you are going to mark as absent. Here the general instruction. Now you can go through different textbooks that are given to you, like book of Doblin or book of Nakra Chaudhary or any book of measurement, and you at least get yourself known how the systematic or cumulative errors are accounted, and how the numericals are to be solved based on that, and how the random errors are to be accounted, how we find out the random error into the given measurement entities. Right. So with this, I think we'll be able to stop here for today. If there is no doubt, I think we'll be stopping here. Any discussion from your side to be made? Let me know anything that is not clear to you till this point of time. Okay, let me know how was the test number 1. So similarly, there will be test number 2 and 3 in the next week. Sorry, not next week, this week only. Based on the same figures given to you, you have to study those carefully. Now here there will be next test number 2 will be based on identification of the inputs, desirable input, modifying input, and the methods of reducing those. So you try to find out what can be the different kinds of input that are going to act in the given measurement systems that are already given to you in the form of figures. What is going to act as a modifying input, interfering input, why it is so, how that can be reduced. At least you can have guess on reading the equipments. Right. So I think I will stop here for today. Thank you for joining.